This is our Sparkyville Power Plant project proposal.
My name is Tanner Mary.
My name is Uri Sharma.
My name is Benjamin Ganick,
And my name is Giovanni Choi.
and this is Team 8.
Alright, so for the problem statement, Sparkyville is in need of a power source due to recent growth in demand of energy. The city, they're leading an expedition in SPP, which is Clean Energy Power Plants, in which the government is providing funds in order for a private source to come in and build this clean energy power plant to help the city. However, they hope to put this in multiple cities if we can design a prototype. So that is our goal within this. In terms of requirements, we must be able to connect this power through the power lines that already exist. And it must fit within the current environment of Sparkyville. So that is a big requirement for us. As mentioned, it does have to be renewable energy sources. So we can't do anything like coal power or anything that would really hurt the environment. And it has to be clean energy. That's why we decided to go with things such as wind, solar, hydroelectric. We should be able to design this in order to fit different environmental constraints such as different levels of lighting, wind, different levels and pressures of water, etc. In terms of the size, the pop-up power plant to scale must fit on a 1 foot by 1 foot board, and it must be shorter than 2 feet in height, and the actual structure itself can extend further than the 1 foot by 1 foot lot. However, it can only extend by 6 inches in each direction. Another condition is that the actual power plant itself has to be freestanding without anything to hold it up, and it must be able to fold into a space of storage provided to us. In terms of our design goal, we want to build an effective and efficient power plant that uses the maximum amount of energy in order to supply the city, that fits within the size constraints and produces steady power and can be integrated not only in Sparkyville, but in multiple cities that are in need of extra power to be generated.
Our proposed design consists of 3 energy components. We will be using wind, solar, and water-based electricity. We will be creating wind-based power through a windmill, and solar power through solar panels, and a water wheel for our hydroelectric energy. The water wheel will extend the dimensions of the base by about 4 inches on one side, and the base will then extend upwards with a frame for 1 foot high, and the top struts will allow the solar panels to be located at the top of our solar panel, closest to the lights. Next, the windmill will be placed with a small gap from the frame to allow the rotation of the windmill to create maximum energy. One design flaw that we foresaw with this design process was the spillage of water from our hydroelectric water wheel. At our total budget right now, we stand at $21.20. As you can see in the picture, our solar energy is mounted at the top of our power plant to ensure that we get maximum light available. Our water wheel is mounted on the side so we can collect the maximum amount of water, and our wind power is mounted in the front, closest to the fan, so we can collect maximum wind. This is all to ensure that we have the maximum amount of power available to us to power Sparkyville.
Wind turbines were first used in ancient Persia around the year 500 AD. These were primarily used for processing grain into usable flour. Now, commercially, they're used for converting kinetic energy in atmospheric fluids into electrical power in strips called wind farms. These wind turbines are used heavily in the northwest, and with regular maintenance are considered very reliable and energy friendly. Wind turbines basically function off of the air pressure differences on the blades of the turbine. What you really have is a very high pressure in the beginning of the turbine that then causes the turbine to be pushed, well, really the propellers of the turbine to be pushed where there is lower wind pressure. Now, the amount of power generated by the wind turbine is primarily related to the rotor sweep area, basically the area that the rotor travels, along with the air density and the cube of the velocity. Fundamental equations that fall into this big power equation for wind turbines are the kinetic energy, the power equation, and the mass flow rate, which we took from MIT sources. So, the water wheel. The amount of power available that is generated by a water wheel is related to the mass of water that falls on the water wheel and the lever arm, that is the diameter or really the radius of the water wheel. Water wheels have been used for centuries. Their first settings come from ancient Egypt, and they've been used in every single major society since then. Fundamentally, water wheels convert energy from flowing or falling water into the useful forms of power. In this day and age, water wheels are primarily used in water turbines, which are used to generate clean energy from most of the time either dams or flowing bodies of water. This is exactly how we plan on using it, and is therefore relatively reputable.
Our final form of energy that we used is the solar panel. This was developed within the last 50 years and successfully implemented in the last 20. These are usually used in large-scale projects such as farms to generate a lot of power, and is dependent on the amount of shading from sunlight near the panels. They optimally have a total sun coverage of as long as possible to provide as much power as possible. The photovoltaic cells function off a phenomenon recently discovered in physics that generates electricity by exposing semiconductor materials to sunlight. The equation of this relates to the area of solar panel, intensity of light, and the efficiency. The increased sunlight intensity and time exposure results in more solar power created. The optimization of these technologies are still very far-fetched, and there has to be a lot of research conducted in order to make it as efficient as possible.